This is the last chapter in C2 on integration, and it builds upon everything that we have done in C1. So what we're going to look at is integrate simple functions within defined limits. We have an upper limit and a lower limit, and this relates to integration to find areas under curves. We can then extend that and look to find the area between a curve and a line through integration, and then we can do an approximate area using the trapezium rule. And the trapezium rule, the formula, is actually in the formula booklet. Thinking back to integration, this integral of integrate 3x squared with respect to x, that's what the dx means, and we don't have any numbers on this integral sign. It's what's known as an indefinite integral. So when we integrate it, it's simply add 1 to the power and divide by the new power. And with indefinite integral, you've got to remember to add the constant of integration. So add 1 to the power, divide through by the new power, and remember your constant of integration. And then we simplify that, so the integral will be x cubed plus c. And if we're given values of x and y, I could actually say if that was y, then we can find out what that constant of integration is. Definite integration is finding out an area under a curve, basically. And if we look at the diagram below, we can see here that we have got a curve, and we want to integrate this function between the defined limits of 1, which is here, and 2. So what we're actually doing is finding that area there. Now how can we do that? Well, we can calculate the area from 0 to 2 and then subtract the area from 0 to 1. So this is called the upper limit, and then you minus the lower limit and it gives you the area in between. So this one is the lower limit, and this one here is the upper limit. And by substituting these values in, we can actually find out the area under a curve. We use square brackets. So when we're doing the calculation, we've got square brackets. The upper limit goes on the top of the bracket. The lower limit goes to the bottom of the bracket. We then substitute in 2, so it would be 2 cubed. So that's the upper limit area minus the lower limit area. So we pop 1 in and it's 1 cubed. So that 7 is actually the area between 1 and 2 on the curve y equals 3x squared. We could say units squared, but this is what's called a definite integral. We do not need a plus c here because we've actually worked out the area under a curve. Let's look at an example of this that we can do together, a couple of them. We have, now it says evaluate, and as soon as you see evaluate, we need a numerical answer. We want a value. And we think about that as to the power of x to the 2, x to the power of 1. We add 1 to the power, so we need our square brackets. Add 1 to the power, divide through by the new power. Add 1 to the power, divide through by the new power. And this was really x to the 0, so it becomes x. And that's in between 1 and 4. Now I'd be tempted to tidy that up a little bit and also put in root signs, because otherwise it's going to be a little bit tricky. So we can use our calculators as well. So we get x squared minus 2 and it's the square root of x cubed plus x, and that's in between 1 and 4. So what does it look like? Well, in the first bracket is your upper limit. So we take this upper limit and we substitute it into each term. And then we subtract the lower limit by substituting into each term as well. So we get 4 squared minus 2 times root 4 cubed plus 4, and then subtract the lower limit, which is 1 squared minus 2 times root 1 cubed plus 1. If we work these out, it'll be 16 minus 16 and plus 4. And in the second bracket, it's 1 minus 2 plus 1. So we get 4 minus 0, which that gives us 4 units squared. The unit squared is not entirely necessary, but it's useful to show that you know that it's the area under a curve. Looking at the second one then, for part B, we want the area between -1 and 0. So it's always the largest number that goes on the top of the integral sign. So we add 1 to the power, which is 1/3 plus 1 is 4/3. So that's add 1 on is 4/3, divide through by the new power, which is 4/3, minus x. Oh, I've forgotten to do something there. Hold on, let's just take that away. I've made a classic mistake there. And that classic mistake is noticing that I haven't actually squared the bracket. I've just gone straight about it and done inside the bracket, so that's totally wrong. Let's try that again. So to do that, we're going to have to expand the bracket. So if we square the bracket, it's square the first one, which is x to the 2/3, double the product, 2x to the 3rd, and square the last one, which is plus 1 dx. So what I didn't see was that squared term there. We must put it in a form where we've got individual terms so that we can actually integrate. From there then, we get add 1 to the power, which is 5/3, divide through by the new power, square brackets because it's in a definite integral, add 1 to the power, which makes it 4/3, divided by 4/3, and then the last one's going to be x, and that's in between -1 and 0. I'm going to tidy this up a little bit, makes the numbers easier. So we get 3x to the 5/3 all over 5 minus 3x to the 4/3 all over 2, and then plus x. Right, show the substitution. So in the first bracket, we're just going to have 0 minus 0 plus 0, and then substitute in -1. It's going to give me minus 3/5, minus 3/2, and -1. So altogether, that's going to give me minus 31/10, which is equal to 31/10, or we could write it exactly as 3.1. So you do have your calculator in this module for C2, so I would check just to make sure. What I'd like you to do now then is exercise 11a, all of question 1 and 2. So 1 and 2. I've got the answers below, as you can see there, so pause the video, and then once you've had a chance to do those, take you a good 10-15 minutes, turn the video back on and then you can check your answers. Welcome back. So checking your answers, I've put the full working there and then I've got the numerical ones after. So this is question 1. You can see there. This is question 1. And then moving further down, got C and D, check your working. And then moving on to the next page, you've got E. Now you can give your answer as a decimal if it can be expressed exactly, a top-heavy fraction or a mixed number. On question 2, check your answers there please. And then on C, there's a little bit, I need to go on to the next page for the final answer so you can see if you've integrated it properly. Substitute your limits in and then that should say question 1, I think. We should have question 1 should say question 2. And then you can see the solutions for the ones at the end there, C, D and E. If you just want to check them numerically, that's what they look like, each question. It's left as a mixed number. The next section so we'll substitute in our upper limit, which is 4, so it gives us 32 minus, well that's just x squared, so that's 16, minus 4 cubed over 3. That should look more like 4 cubed. So 4 cubed over 3, and then if you put 0 into all the others, just as 0, and that works out to be 80 over 3, which is acceptable, or 26 2/3, and that's units squared. So when you're given boundaries as well, identify the area on your curve, identify your lower limit and your upper limit, make sure that your curve is in a form that you can integrate it, Substitute your upper limit in, take away your lower limit, and then you get a numerical value at the end. So to practice this, I'd like you to have a look at the next page, which is exercise 11b. There's a couple of questions here to do. So question 3, and then I've taken another one from the mixed exercise, which is also a question 3. And then you can use integration. It does say on this mixed one use calculus. We've got minimum points. So differentiation and integration can be together within the same question. So I'd like you to try those two questions. Again, pause the video. The solutions will come up on the next slide, next part of the video. And then from there, we'll go on to areas below the x-axis. So the solutions for these two questions, well, it's question 3 is 6 units, and for the mixed exercise for A and B, you've got the two solutions there. Right, moving on, we've got area below the x-axis. And this is quite important that you identify in your curve if you do have any area below the axis. Now, the one thing that you've got to notice, that any areas that are below the axis, so area B, will actually give you a negative answer. So therefore, when you work out of area B, you've got to do what's called the modulus of it. So we'll get a negative answer, but then if we have a number, say, minus 4/3, and we take the modulus of it, then it's actually 4/3, because that negative sign in there just tells you it's below the x-axis. It only tells us the position, so we're actually interested in numerical value, and to do that we take the modulus of the number, and that allows us to just take the numerical value. So what we've got to do here is actually work out the area of A and B separately and then add them together. So that's really, really important that you remember to do that when you see an area under a curve. So what we can see for area A is this part here, and it starts at 0 and it goes to 1, and then B goes from 1 to 3. So the two parts that we actually want, for area A, it's in between 0 and 1 of the curve, which is x squared minus 4x plus 3 with respect to x. And for area B, it's equal to in between 1 and 3 for the curve again, x squared minus 4x plus 3 dx. So once we do that, we get add 1 to the power, divide through by the new power. The next one is going to be 2x squared, and then plus 3x, and that's in between 0 and 1. If we do the sat to the same for B, x cubed over 3, 2x squared, and plus 3x, and we'll put that in between 1 and 3. So if we calculate these separately, we're going to get for this one. Right, substitute 1 in, we get 1/3 minus 2 plus 3. Put the lower limit in and we're going to get 0. So altogether that works out to be 4/3. If we then put in our B limits, we get, putting in the 3, we get 9 minus 18 plus 9. And if we put 1 in, we get 1/3 minus 2 plus 3. And if we add, take those both values together, it gives me minus 4 over 3. So that confirms, the negative sign confirms it's below the x-axis. So what we want to do is the area is actually equal to the modulus of minus 4 over 3. So it's just 4 over 3. So the total area that we want is A and B added together. And that's equal to 4/3 plus 4/3, which is 8 over 3, which can be left like that, or 2 and 2/3. So always try and put it in an exact form. Right, let's look at the next one. You may or may not be given the curve, and the next example is one where you're not given the curve at all. So we're going to have to multiply it out at some point. So if we take y equals and then multiply this out, we're going to get x times, it's going to be x squared minus x plus 3 gives me plus 2x squared. Sorry, 2x, and at the end will give me minus 3. So the actual curve is x cubed, 2x squared, and minus 3x. So that's what we're going to have to do to integrate to get the area. So it's telling us to find the area of the finite region. That just means that it's bounded, it has a definite area by the curve and the x-axis. Well, we don't know what it looks like, but if we see here, we've got a happy ending x cubed, so it's going to look like that. And if we let y equal 0, that will give us the roots on the x-axis. So if we pop those in, we get x is equal to 0, could be equal to 1, and could be equal to minus 3. So that's our 3 points on the x-axis that the curve is going to cross. So let's see what we can draw here. So a little sketch of what it's going to look like. And it's going to come up at minus 3, go through the origin, come back down again. I don't know about the symmetry of it, it's just a rough guess of what it looks like. Not drawn that very well, it's too much on the right hand side. But we want this area, so we'll call that area A, and then we want B as well. So if you notice, B is below the axis, so we can't add them together. We can't just go from minus 3 to 1. We've got to do two areas and then add them separately, so that because B we know is going to give us a negative area. So let's go about finding the two separate areas. Right, for area A, it's going to be from minus 3 to 0. Remember, 0 is bigger than 3, of x cubed 2x squared minus 3x dx. So let's integrate that. That's x to the 4 over 4 plus 2x cubed over 3 minus 3x squared over 2. And that's in between minus 3 and 0. When we substitute that in, and keep that there. When we substitute that in, if we put 0 in first of all, we're going to get 0. And then the second bracket's going to be 81 over 4 plus 54 over 3. I think that should actually be minus. Yeah, that should actually... Oh no, it isn't. It's a plus, isn't it? I'm just looking at the wrong thing, sorry. So that's a plus, and then if I put minus 3 into... I think I should... If I substitute minus 3 into there, I get minus 27, so that is definitely going to be a minus. And then we're going to get... put minus 3 into there, that'll give us minus 27 over 2. So watch out for your signs, because we've got a minus 3 cubed gives me minus 27. So I've got to be careful with that. Right, what does that give us then? So what we get is 0 minus 45 over 4. So the area of A is 45 over 4. Looking at B, it's going to be the integral from 0 to 1 of the same thing, x cubed plus 2x squared minus 3x dx. And then if we put that into a square bracket, x to the 4 over 4, 2x cubed over 3, 3x squared over 2. Then substitute our limits in from 0 to 1. And if we put 1 in, we get a quarter plus 2/3 minus 3 over 2, and then in our second bracket it's just going to be 0. And then when we add that up, if you can do that, we are expecting a negative answer. And we do get minus 7/12. So we have to take the modulus of that, so the area that we actually have is 7/12. So the total area is A plus B, so it's 45 over 4 plus the 7 over 12, and that works out to be 71 over 6, or 11 5/6 units squared. So just to point out again, if you are not given the graph, then you have to do a sketch. We've got this bit above the x-axis, which is fine, it's a positive area, but as soon as you see something that is below the axis, you've got to treat these two areas completely separately. You will find that the one below the axis is a negative, and then what we've got to do is take the modulus of it, so the modulus of it to make it into a positive area, and then we've got the full total area added, those both added together. So we've looked at a couple of examples that have the area between the curve and the x and the y-axis. We now look at the area between a line and a curve, or curves and two curves it could be as well, and we find the area that is bounded by the curve and the line. So if we look at the diagram, if we're going to integrate, then that's absolutely fine. So we need the lower limit to be 0, so that's our lower limit. And our upper limit isn't actually the 4 on the axis. This value here is our upper limit, so we'll call that our B, and that's our A, so our B limit, because when we look at it's lower limit at the bottom, at the top, and then if we multiply this out, we've got 4x minus x squared dx. That's what we're looking at. And the line between from A to B of x dx as well. So we could actually work them out separately. We could do, for instance, we could work out the area of this and then take out the area underneath. But a quicker way, or a more efficient way of doing that, is saying that this is the upper curve, and this one, although it's a line, we'll call it a lower curve. And if you take upper curve minus lower curve, and then integrate it, then you've found the area between the two curves. But the key thing that we've really got to find is this point of intersection, which is our upper limit. So to find B, we solve them simultaneously. So x is equal to 4x minus x squared. Take everything onto one side. So we're going to get x squared minus 3x is equal to 0. Factorise that, we get x minus 3, and we can see that x can equal 0, but it can also equal 3 as well. So b must be equal to 3. So we've got our limits now. So it's upper curve minus lower curve, and this is not given to you, so you have to actually memorise this as well. So a to b of the upper curve minus lower curve dx. Right, so what we put in then, we've actually found our limits, and they go from 0 to 3, and the upper curve, the one on top, is 4x minus x squared, and that's take away the lower curve, and I'll put it in brackets because we've got this minus sign here. Just watch out for it in case we get a double negative, and dx. So when we simplify that, we get the integral from 0 to 3 of 3x minus x squared dx. Integrate this, we get add 1 to the power, divide by the new power, and x cubed over 3, and that's in between 0 and 3. Substitute our values in. 27 over 2 minus 27 over 3, and our second bracket is going to be 0. We pop that into our calculators, we get 9 over 2, or it can be 4.5, or it can be 4.5. As long as that decimal can be expressed exactly, you can write it as a decimal. Otherwise, if it's a third or a sixth, just leave it as either a top-heavy fraction or a mixed number. So looking back at what we've just done, we've got a curve and a line, and the easiest method for this one is to take this upper curve minus the area below this lower curve, so subtract them, and then work out the area between them, which is this yellow region here. We're not given the limits. Don't be tempted to use 4, because it's actually where the line and the curve, or two curves, meet that you get your upper limit. We then move on to do the algebra, and your algebra is your upper curve minus your lower curve, so we simplify that to 3x minus x squared. Integrate, substitute our upper limit and then our lower limit, and then we've got the area between two curves. So that's what that actually represents, is the area between the curve and the line. What I'd like you to do is to practice this. If we look at the next exercise we have here, if we look at the diagram that we've got, we can see once again we've got an upper curve here, and this is a lower curve. So you're going to have to find this lower limit, and then this point here is your upper limit, so that's your lower limit, which is A, and that's your upper limit, which is B. So you've got y equals 4 minus 4x, and the upper curve has the equation, it's a cubic there, so if you solve them simultaneously, you're going to come up with the area between them. It does actually give you the points A and B, so that's actually quite useful. You don't have to do intersection, I didn't read the question. So if A is the point minus 1, so that's going to be minus 1 there. So your upper and lower limits are going to go from minus 1 to 1, so that's one part. And your upper limit is 9 minus 3x minus 5x squared minus x cubed. And then you've just got to take away your lower one, so 4 minus 4x dx. And that's where I've said be very careful, because we've got a double negative here. tidy up the algebra of it, and then you can work that out. You're looking to get an answer of 6 2/3. So work your way through that one, please. The other question that we've got is mixed exercise, so 5, 6 and 8. If you can see, 4, 6 and 8. If you look at 4, you're going to have to multiply this out first of all, and then use your answer in part 8 to evaluate that. So this one's your indefinite integral, then put your limits in, and you give your answer as an exact fraction. So we don't want any decimals at all in this one. We've got this formula, this equation rather, and we have to show that y is equal to that. Well, we're going to have to square both sides on this, so square and then square this. But remember, when you square the right hand side, you're going to get y to the half all squared, but then you're going to get a bracket, so it's to the third plus 3 and square it. And that means that you're going to get a middle term and an end term, so you can see that b is going to be 9. Hence find the integral. So that's an indefinite integral. And I know it's an indefinite integral because I don't have any limits on it, so you need a plus c for that one, and then use part b to do a definite integral. And then question 8 is a past exam question because it's got an E on it. And you'll see once again that this is our upper curve. And this is, although it's a line, it's a lower curve. And we've got to get these points. We can say our lower limit is going to be 0. We don't know, we've got the x coordinate of n is 2.5, so that's going to be our upper limit. And it doesn't matter that it goes below the axis on this one. As long as you do upper curve minus lower curve, then you're absolutely fine. You can work it out with that. Moving on to the next one. We've got a diagram here. You're asked to differentiate, show that dy by dx is equal to, so again let's bring in integration and differentiation together. That's what happens in C2. You get a calculus question of everything together. And at the point B on the curve, the tangent to the curve is parallel to the x-axis. So that should actually tell you, if it's parallel to the x-axis, that B is actually a maximum turning point. If it's parallel to the x-axis, then this tells me that dy by dx is actually equal to 0. So I'm taking out some of the information from the question then. So we can find out the coordinates there. And then we want to find the area to 3 significant figures. So it's giving you the degree of accuracy. So you're actually going, the area that you want is from 0 to 12. And your curve is 12x to the half minus x to the 3 over 2 dx. So that's per part C is what you have to work out. Right, this should take you quite a little while. I would say a good half hour. I suggest you have a go at these questions, especially exam type questions at the end, and then I will reveal the answer to you. So pause the video, have a go at these, and then I'll give you. So welcome back. That's question 3 for exercise 11D. And then moving on the mixed exercise 4, 6, 8 and 9. There's the answers that you should have got there. Any problems about that, just come and see me. Right, the last part is the trapezium rule. And this is a numerical approximation for the area under the curve. Now, unfortunately, if I ask you this year to integrate 2 to the x dx, and it was in between the limits that we've got there is minus 1 and 3, it'd be quite impossible. So what we do is we introduce a numerical method, because there are going to be times when you get a curve that you can't actually you can't integrate. So you've got to actually take strips, and it's called the trapezium rule because if we look at the diagram, I've zoomed in on it a little bit further down. If we zoom in on it there, if we take some strips here, so say I take 1, 2, 3, 4 strips, so let's make a different colour. If I make it up of strips like this, if I go from there to there, and there's another strip, and I go from this part and work out the area of these trapezia, you can see it's above the line, these are supposed to be straight lines, so I've got that there is a trapezium. And what we're doing is if we work out the area of that trapezium, because we can get the y coordinate here and here for when x equals 1 and x equals 2, then I can work out the area of the trapezium, for which you know the formula from GCSE. So this is the reason why we use the trapezium rule, and this is used again in C4 for next year. So we need to know this inside out. The formula is given to you, but you must know how to actually apply it. So the trapezium rule is for the area between A and B of the curve dx. It's equal to the height divided by 2. Now the height is the width, actually the width of each strip. Then your first plus your last plus twice all the ones in between. So y2, y3, all the way up to yn minus 1. Now this will make a bit more sense when we actually start to use it. So we'd have, that would be y0. This would be your last one, which is 0, 1, 2, 3, 4. That would be y1, y2, and y3. And we get these values. These values are called ordinates. And what we've got here are 4 strips. So that actually generates 5 ordinates. And if you think about it, these sides of the ones in the middle are actually being used twice to work out the area of each trapezia here. So that's the formula. It's given in the formula booklet, and we can use it to do numerical approximation of the area under a curve. So let's apply it. We can use the trapezium rule to estimate the areas given by the integrals given our answers to 3 significant figures. So the curve that we've got, we're going to use 4 strips. So as you can see, we're going to get 5 ordinates. So this is going to be y0, y1, and so on. So I'll put that underneath. That's going to be y0, y1, y2, y3, and y4. And that corresponds to the strips that we're using here, y0, y1, y2, y3, and y4. And then if we are using 4 strips, we're going between 0 and 1. So each of the width there, it'd be 1 minus 0 divided by 4. So the width of each strip, or the h, is equal to 1/4. So we've got to work these out. So we substitute our value of 0. So when x is equal to 0, we want the value of the root of 1 plus x will give us our y0. So So that tells me that y0 is equal to 1. If we do that in the same way, then we'll substitute in x equals 0.25. We get the square root of 1 plus 0.25, and we'll get y1 is equal to 1.118. So 1.118 goes in here. When x is equal to 0.5, we substitute it into 1 plus the x square root. So that tells me that y2 is going to be 1.225, and when x is equal to 0.75, substitute it in again and we get y3 is equal to 1.323, and then y4, the last one, when x is equal to 1, is equal to root 2, which is 1.414. So we pop these into the table, and this actually helps us to calculate the trapezium, the area under the curve, using the trapezium rule. So that's 1.414. Okay. If we take these values then, our trapezium rule is the area under the curve is the width, that's approximately equal to the width between the strip, which is h, so that's our h there, divided by 2. Then our first ordinate plus our last ordinate, which is y4, plus twice everything in between, which is y1, y2 and y3. Now if we substitute the values in, that's what we're expected to show. So it's equal to 0. Sub our values in. So the distance between the width of each strip is 0.25. Divide by 2. Our first ordinate was 1. Our last one was 1.414. And then twice the middles. y1 was 1.118. y2 1.225. And y3 1.323. Pop that into a calculator and see what we get. So when we work that out, we get 1.21825, and we want the answer to 3 significant figures, so that's approximately equal to 1.22 to 3 significant figures. So make sure that you can locate this formula, which is called your trapezium rule. In the formula booklet. So it's your, if we just go through what we have, the distance between the strips, so h divided by 2, your first ordinate plus your last ordinate plus twice the sum of the middles. And then you can see from the table how we substitute that in. And that's simply because we really don't know how to integrate the square root of 1 plus x. So we need to do numerical methods to help us out with this one. Right, this one, second example, we've got using 4 ordinates. Now 4 ordinates means that there must be 3 strips. So that's what that part's telling me, is there's 3 strips altogether. So if we look at the diagram that we've got, we can work out the values between 0 and pi by 2. Now we have to work in radians. Really important. So you can see there that each of these is a radian measure, so you must make sure that your calculator is in radian mode. So we fill in the values of these. and we have using the cos of x. So as you can see from the diagram, we've got 3 strips and we're going from pi by 2 to 0, and we've got to divide that through by 3, so we know that each one is at pi by 6. So that's pi by 6, 2 pi by 6, and then 3 pi by 6, which is just pi by 2. So that one there is actually equal to pi by 3. So on your calculator, if you put these values in for x, you will get your y0, your y1, your y2, and your y3. And we can see that from our diagram. So working out the area from this again, using the trapezium rule, the area is approximately equal to the width between each strip divided by 2, multiplied by the first ordinate, and our last ordinate is y3, and twice the middles, which are y1 plus y2. We'll substitute our values in. H is pi by 6, and that's all divided by 2. Y0 is 1. Y3 is 0. And then 2 times the ones in the middle, 0.8660 and 0.5. If we pop that into the calculator, see what answer you actually get. That gives an answer of 0.977035, etc., etc. So approximately, we'll give it to 3 significant figures, so 0.977 to 3 significant figures. That's the area in 3 strips. Now to improve that area, you would see that we should actually increase the amount of strips, because then we would get the top of the trapezium, if we have a look at it, the top of the trapezium, if we made smaller strips, would actually get closer to the curve itself, rather than this one's going quite a bit underneath, so we've got an underestimate for that one. So if we look back at what we got there, we can see that's using the trapezium rule. Well, there's a few questions here for you to do as well, so these have to hand in on file paper. It's using the trapezium rule, and what usually happens is we have a table of values and you're asked to fill these in. So this is your y's are called your ordinates. Then you can see here that our h is 0.2, so we can put that into our formula. But the key thing is you must quote the formula that you're going to use and then substitute your values from your table and then give it to an appropriate degree of accuracy. So if you get those, there's quite a few questions there. There's 1, 2, third one. So 3 questions based on the trapezium rule, because these functions can't be integrated with what we've used before.